Hello everyone. Today I'm going to talk about hypothesis testing for one population proportion. I'll just remind you that statistical inference is the process of using the sample data to make predictions about the population. So do you remember we have buzzwords for these things? What were we calling the sample data? And also there's a buzzword for the population. So the numerical summary of the sample data we were calling the statistic, and the numerical summary of the population we're going to call a parameter. So since we're talking about proportions here, the statistic is going to be p hat, which is the number of successes divided by the sample size. And the parameter is just going to be p, and you remember that the concept here is that this is unknown. So hypotheses, both the null hypothesis and the alternative hypothesis, they're statements about parameters. Okay, so the null hypothesis is always some claim about the population, and whatever the number is in that claim, we're going to call P0, and then there's three different choices for the alternative hypothesis, claiming that it's greater than what the null hypothesis says, less than, or not equal to. I have an example here about streaming video. So let's just write the null hypothesis and alternative hypothesis in this case. So in a situation where you're talking about things changing or something being different than it was in the past, the benefit of the doubt is always going to go to the status quo. So what that means is, since usually 34% of individuals use streaming video, we're just going to go ahead and assume that it's still 34%. Obviously, so we think the rate has increased, so we need some kind of alternative hypothesis here. What's the other idea? So the other idea is that it's something more than 34%, so the alternative hypothesis will be 34%. The alternative hypothesis, will be that p is greater than 34%. So in a situation where you're asked whether or not something is changing, the benefit of the doubt, the null hypothesis, is always going to be that there's no change. Okay, so a few other common examples are clinical trials. So if a researcher is checking to see if medicine works, then the benefit of the doubt is always going to go to the medicine having no effect. And if someone is making a claim, like if Apple claims that 99% of college students have an iPhone, even though that's an outrageous claim, the way that we go about arguing that they're not correct is by giving them the benefit of the doubt. So if somebody makes a claim and you're going to try to test that claim, you give them the benefit of the doubt. The second part of hypothesis testing is what you do once you go and collect the sample data. So the sample data here is going to be p hat, x over n, so that's what we have here. The number of successes divided by the sample size, so this is the rate of successes in the sample. And then there's two possible outcomes here. In the first scenario, I've made it so that the sample data is very far away from the null hypothesis. So if this number here was 34%, then maybe the larger the percentage gets away from 34 in our streaming videos example, the farther that p hat would have to be plotted on this normal curve. So the two ways that we measure how far these things are apart is with the z-score. You can see here as p hat moves farther and farther away from p0, as what you're getting gets farther and farther away from what you're expecting to get, then this z-score will get larger here and this p-value will get smaller. So in these two examples, this is an example where we're not getting what we expect to get. So this is the situation where h0 looks false. We doubt h0. I'll write that. We doubt that h0 is true. And in this situation down here, we can't doubt. We can't doubt that h0 is true. Because even though we got something that we weren't expecting, it's still kind of a likely event because this p-value here is so small. Is so large. All right, so let's go and fill this in. Everybody's favorite statement. You can see the farther that the farther that the sample data comes in from the null hypothesis, from the proportion in the null hypothesis, the smaller the p-value gets. The p-value is the probability of getting p hat or anything that is more extreme than p hat. I know that that's kind of a mouthful, so you're just going to have to take it for what it is right now and come back to it later. If you're not really 100% on that, that's okay. It takes a while for this concept to really sink in. Okay, so the next step in hypothesis testing here is pretty simple. If the p-value comes in less than the level of significance, remember we almost always use 5%. That's just kind of the standard thing that we do. Really, this corresponds to level 2 on the empirical rule, so that's where they're getting this 5% number. You may remember the 95% number from our confidence intervals. So these are just areas in the tails here instead of areas in the middle, like with confidence intervals. So the rubric is pretty simple. Would you calculate a p-value if it comes in less than the level of significance? So if you're getting a really small number, then what you're going to do is reject that null hypothesis value. So the two choices are you either reject or you don't reject. So this is like in court when you find someone guilty or not guilty. So rejecting, that's the equivalent of guilty. Remember that the null hypothesis is that the person is innocent. And then not rejecting, this is like not guilty. So you reject it when you find someone guilty is when you do have evidence, and when you find someone not guilty, the reason that you find them not guilty is because you don't have evidence. So when you reject the null hypothesis, you do have evidence, and when you don't reject the null hypothesis, that's when you don't have evidence. Okay. And then this level of significance, you always just get it from the context of the problem. It's pretty often going to be 5%. And then also you're always going to need to include the context, so whatever the problem was about. So in our motivating example here, this was the rate of individuals who use streaming video. So that's what you'd say here, the population proportion of individuals using streaming video services is. Now, in court, the results are always either guilty or not guilty. So you never make results about people's innocence. So in court, they always make results about a person's guilt. So similarly, in hypothesis testing, we always make results about the alternative hypothesis. So what goes here is always the alternative hypothesis. Okay, so in this example, we're going to be considering an online class, and an instructor is kind of trying a treatment here. So this is similar to the problem about, testing a medicine, except in this class, the medicine is these mandatory videos. So like maybe you have to watch the video before you can do the online homework or something. And the regular online pass rate is 72%. Test the hypothesis at the 5% level. I should be more specific here. Okay, so we're going to test the hypothesis at the 5% level that there is a difference between these two classes, the regular online classes and the classes that have these mandatory videos in them. The null hypothesis here is going to be that there's no effect, that the mandatory videos don't make any difference. So if the mandatory videos don't make any difference and the pass rate is 72%, then the pass rate in this guy's class is also going to be 72%. Now here's the buzzword here, the difference between the two classes. So what we're going to do is test the hypothesis that his pass rate is not equal to 72%. You push the stats button and then you go over to the tests option, and then one prop z test is number 5. So P0 is 72%, and then our number of successes in this problem, the online pass rate is 72%, and then 64 out of 200 students in the mandatory video class passed. So this is 164. And then there were 200 students in this mandatory videos class. And I'm going to leave the alternative hypothesis here as not equal to. So let's calculate this and see how it comes out. Okay, so that was pretty promising there. So what we ended up with is a z-score of 3.14, and it's almost pi there. That's freaking me out. So we got this very, very big z-score outside level 3, and then we got this very, very small p-value. Okay, so in this situation, the null hypothesis is 72%. So in the distribution of the samples, what we would expect to happen is to have samples coming in at 72%. And then we didn't. Actually, we found p hat here to be 164 out of 200, which is where this 82% number comes in. So that's like way over here is 0.82, and then we were just left with a tiny little shaded value right there, and you can see this z-score is 3.1. Let's just round that, 3.1. Now I want to point out a subtle detail about this. Because we're checking the alternative hypothesis is just different than, what this means is any result different than 72% is going to make this 72% number look wrong. So this time we got a result where the students were doing much better, but that's not necessarily always what has to happen. It's also possible for us to get very, very extreme results. If the mandatory videos ended up really hurting the students and made the pass rate a lot lower, then we could have ended up with a result way over here, and that would have also rejected this 72 number. So what you do is you need to consider both possibilities when you're calculating these p-values. So actually this total area in both pieces here, that total area is 0.0016, which is incredibly small. So let's move on to the next step. So the next step here, we're going to have to decide if the p-value is less than the level of significance. Okay, so our p-value is incredibly small here, 0.0016. So is that less than 0.05? Yes. Yes, it is. So this means that we are going to reject H0. So yeah, we are rejecting the null hypothesis in this case. So I just want to touch briefly on, in this context, what the interpretation of the p-value is. What we did was we assumed that the true population was the true rate at which students would pass is 72%, even if they were watching the mandatory videos. And then what we got was 82%, which is very different than 72%. And there's two explanations for that. One is because maybe the mandatory videos helped. And then the other one is because maybe this was just random chance. Maybe we just happened to randomly select a bunch of really strong students to end up in this class. But the probability that of this happening just randomly is so small that even though we do have a little bit of doubt that it is the mandatory videos, the amount of doubt that we have is so small that it's beyond reasonable. It's not reasonable for us to use this level of doubt, 0.0016. I'm just going to live with that amount of doubt. So what we're going to do here is reject the null hypothesis that the pass rate in the mandatory videos class, we have evidence that it's not 72%. Okay, so because the p-value came in less than the level of significance, this means that we are going to reject the null hypothesis. So we do have significant evidence, and you can see here the context, the population pass rate. So this time I use the language of rate because this isn't, it is a proportion, but sometimes I like to talk about proportions as rates. And then what is the conclusion going to be about here? Remember, the conclusion is always about the alternative hypothesis. So we have significant evidence at the 5% level that the population pass rate of students that watch mandatory videos is different. One thing that I just want to caution you about, a lot of students get stuck in this, is I don't know where this comes from, but it's really tempting right here to try to make conclusions about the sample. We don't need to make any conclusions about the sample. The sample, I know exactly what it is doing. The sample was 164 out of 200. There's no hypothesis necessary about that. So every time we write a conclusion to this, it's always about what the population is doing, because that's the parameter and that's the unknown object.